Hi, welcome to the screencast for 10.2, 10.3, and 10.4. I'm going to attempt to cover all three of these sections in one screencast, although I may have to split it into two. But 10.2 starts out looking at alkanes, and alkanes are represented with the formula CnH2n plus 2. There's no functional group per se. There's not an OH at the end or a COOH. So I think of hydrogen as the functional group that instead of putting an OH or anything else at the end of that last carbon, you just go ahead and put the third carbon. They're called a saturated hydrocarbon because they contain just hydrogen and carbon, and they're all single bonds. There's no place for anything else to be added. So that's what saturated means, is it can't hold anymore. Carbon can't hold any more bonds. It's got four single bonds on every single carbon. Because of this, because they're all single bonds, they're fairly strong bonds, and they're also nonpolar bonds. So this means alkanes have low reactivity, so they're very stable, which means we can compress them, like propane gets compressed into liquid propane. You might have heard of LP gas. That means liquid propane. That makes it much easier to transport because it takes up much less space, and yet it's safe. You don't have to worry about it being explosive like you would with liquid oxygen and liquid nitrogen or liquid hydrogen. There's two common reactions that alkanes are involved in. One is combustion, where it combines with oxygen, and that's a pretty common reaction that we use for both transportation and for heating. And then the other one is halogenation, which is just what it sounds like. It's combining with a halogen. And you need to understand the mechanisms of both, so that's what we'll take a look at on this next slide here. So combustion reaction, again, two main uses for it is for it to drive an engine for some kind of transportation or to run some kind of equipment. And the other thing is burning it either to generate electricity in some kind of power plant or burning it to heat homes, etc. And the general reaction is an alkane reacts with oxygen gas and produces CO2 and H2O. Now that's under ideal conditions that only CO2 and H2O will be produced. It's highly exothermic, which is why we use it to generate energy, either for moving things or for releasing heat. And the reason it's highly exothermic is because if you think about it, CO2 is a double bond and H2O is a polar bond, so it takes a lot of energy to make those bonds, and the bond making is on the right side of that enthalpy graph, so there's a big drop in energy as you make those bonds, which would be energy being released. The downside of combustion reactions, even though we use them a lot and they do a lot of great things for us, is that carbon dioxide and water are both what we call greenhouse gases, which means they absorb infrared radiation or heat as it's being radiated back out towards space. So of all the sunlight that comes to Earth each day, a big percentage of that is actually reflected back out to space, and that's why Earth doesn't heat up more and more and more. But now with more and more greenhouse gases in our atmosphere, we're trapping more sunlight than the Earth used to, than Earth's atmosphere used to. And so the Earth is starting to show some effects of that. So it's similar to a cloudy night. The temperature stays warmer on a cloudy night because the heat doesn't escape as easily. It's like putting a blanket over top of us. And so that's what's happening with CO2 and H2O. But you don't need clouds for it to be happening. It's happening all the time because of the amount of those two gases in the air. A couple other things with the combustion reaction is that oftentimes there's other competing reactions. If oxygen is limited, then carbon monoxide tends to get produced with the water, which is called incomplete combustion. And carbon monoxide you probably recognize as being something not desirable. It's a pollutant. And one of the main issues with it is it binds to hemoglobin in your blood instead of oxygen binding there. And of course, if you're not getting enough oxygen, it's going to create all kinds of health problems for you. And if the oxygen is really limited, then burning alkanes can form carbon, and we see this when soot is produced. You maybe have seen soot produced when you're burning a candle or something. That's because of limited oxygen, or it could be because of the type of material used in your candle, but limited oxygen is definitely one reason for soot. And solid carbon is bad because it tends to clog up our engines. The soot, of course, is just nasty. It makes things look gross, but it's also bad for your lungs. And because it gets into the air, some of it stays in the air, and that's when we see smog and the haze. But that's also an issue because it's been linked to something called global dimming, which is it doesn't allow sunlight to reach us as easily. So we've got issues going on all over the place with burning alkanes. Substitution reactions for alkanes are just what it sounds like. They undergo a substitution, which means some incoming species replaces one or more hydrogen atoms. And with an alkane, this actually requires energy. It's an endothermic reaction, so it has to be done usually in the presence of sunlight. UV light will drive this and give it the energy to happen, because remember, the hydrogen-carbon bond is fairly strong, so you need something strong enough to bump that halogen or to bump that hydrogen off. And hydrogen is also, fairly reactive, and it's that small atom pulled in tight to the carbon. So it's a unique process. It starts with UV light, like I said, which is called homolytic fission, which just means to break it apart. So the UV light splits the halogen molecule, so Cl2, Br2, whatever, it splits the halogen molecule into two atoms. And when a chlorine atom, a bromine atom, when a halogen atom is all by itself, it's what's called a free radical, because it hasn't picked up another electron. So it's got 7 electrons, meaning 1 electron's unpaired. There's no charge on the atom. So it's not an ion, but it's a really reactive atom looking to find a partner for that last electron. So you maybe have heard about free radicals with health stuff, because free radicals are linked to a number of health issues. At any rate, this free radical causes a chain reaction to start happening. And the free radicals now are reactive enough to bump hydrogen off from its carbon bond, and it will bond with the alkane. But when it does this, it produces another free radical. So this is a process known as propagation, that the free radical is able to bump a hydrogen off and make another one of itself. So it both uses and produces the same species. And on the next slide, I'm going to show you what I mean by this. But what it means is that one chlorine atom or one chlorine molecule that gets split into a free radical can go through and destroy thousands of ozone molecules, which is exactly what happened to our ozone back in the 70s and 80s. So when you have a chain reaction with propagation in it with positive products, meaning products you want, that's great. But free radicals generally are not good things. And so they're bad things to have in a chain reaction. And like I've mentioned, they've been linked to things such as cancer, aging, and ozone destruction. So the reaction mechanism for homolytic fission or the substitution reaction of an alkane is kind of complex. This is on page 200. And I'm going to try and simplify it, because what IB is going to expect you to know is the 3 steps of this. And the 3 steps are initiation, propagation, and then termination. So initiation is this one. You should be able to remember, because this is when the UV light splits a halogen atom in half. So all you have to know for this is what a halogen looks like before. Remember, they're diatomic. You draw the arrow, and then you put UV light here because energy isn't considered a reactant, since it's not matter, so it just put it ahead. That's a catalyst. And then it's going to split it into 2 of these free radicals. And we show a free radical by writing the symbol and showing that 1 unpaired electron. Now there's 7 valence electrons. The paired ones aren't going to be involved in this, so we don't show the other 3 pairs. We just show that 1 paired electron, so you realize it's not a chlorine ion, it is a free radical. So that's the initiation step. And then propagation, the book gives you several steps to choose from, and it really doesn't matter which one you look at. I'll just go with the first one here, and they're only going to ask you to come up with 1 step showing the propagation. So let me just pause and get this up here for you. Okay, so if you look at the reaction I put up there, again, this is the first one of 4 that they show in the book on page 200. And what I like about this one, I think this is the easiest to remember, because it's taking the product, the Cl free radical, from your initiation step, and we're using that as the reactant down here. You're combining it with an alkane, because remember, this is what it's all about. It's a substitution for an alkane. So CH4 is the simplest of all alkanes. It's methane. And when you do that, the Cl is going to bump off one of the hydrogens. So we can see over here, we only have CH3 left. And then that hydrogen is going to get together with the Cl. And so instead of the Cl replacing the hydrogen, the Cl is just taking a hydrogen to form the HCl, and it's leaving its unpaired electron there with the CH3. So now carbon is the one with the unpaired electron. And so you're left with the free radical, and that's why this is called a propagation, because one free radical produces another free radical. And if you want to look at page 200, you can see how that CH3 then goes on to react with Cl2 to produce more Cl free radical, and then the Cl free radical could produce more CH3 free radical, and it goes on and on. But IB is only going to expect you to know one of these, so this is the one I would go with. And then termination, the easiest one to do for termination is when two of these chlorine free radicals get back together and form a chlorine molecule, because it takes two free radicals out of the system. So initiation and termination are just the opposite. And then propagation, I think, is fairly easy to remember if you think about what's supposed to be going on in this process. Okay, I've got a few minutes left in this screencast, so I'm going to start on section 10.3, the alkenes. And alkenes, the general formula is CnH2n. So they're considered an unsaturated hydrocarbon because there's one carbon-carbon double bond in them. If you can have an alkene or a hydrocarbon with more than one double-double bond, but if there's two double bonds, then it's called a diene. If there's three, it's called a triene, etc. So we're only interested in the alkenes here with one double bond. And remember, a double bond has a sigma bond, which is going to be fairly strong, but then the pi bond has to sandwich around that. Remember the hot dog with the bun sandwiched around it? So the pi bond can be broken pretty easily. So that means alkenes are going to be very reactive at that double bonded site. It's going to easily break the double bond and leave just a single bond between those carbons, but that second bond is going to open up. So that means alkenes can easily undergo what we call addition reactions, where the double bond just opens up and two new species come in there. So hydrogen's an easy one to come in and just now make it an alkane again. But there's also a couple of other reactions that go on. So the first one we'll look at is the hydrogen, as I mentioned. So if you have an alkene, and it would have to be, the smallest alkene is ethene, because CH4 doesn't have two carbons, but ethene is CH3, CH3, so the double bond is between these two carbons. And so if you put hydrogen on with it, it is going to open up and produce C2H8 or CH4CH4, if you want to think of it that way. And again, what's happening here is you've got your three hydrogens, and this bond right here gets broken. And so now you have a single bond between the carbons, and you've got these two open sites where the hydrogen comes in and replaces it. So this is used, hydrogenation is used very commonly in the food industry, because oils, plant oils aren't as solid as vegetable oils, but they're typically healthier for you. Well, we make them unhealthy by doing this hydrogenation to it. We make hydrogenated fats by saturating these healthier unsaturated oils so that margarines will be closer to room temperature or be a soft solid at room temperature. We also use this process to produce what are called trans fats, which are even worse for us than just eating butter. So when we do hydrogenated fats, if you follow the news at all, you know they're getting a bad name now, and that's for a good reason. So then I'm going to continue this screencast and look at the other two reactions, addition reactions. I guess there are other three addition reactions of alkenes. They can combine with halogens. They can combine with a hydrogen halide, which would be like HCl. And then they also tend to combine with water. So I will end this one here and continue on part B.